So we are continuing on our sequence of primers. Now, Pete calls them primers, and I learned that they were called primer, and I think we need to get this resolved, but we don't need to get it resolved right now.
I think it depends on what side of the Mississippi River you're on.
Okay, no doubt. That is.
Or the Charles River.
I see. All right. But today we have a couple of folks from Washington State. Anurag will be leading off with something on smart grid control, and then Carl Hauser, I'm told, will be following up with that. So I'm hoping that WSU is online and ready to go. WSU, are you online and ready to go?
I am. Can you hear me?
I can. All right, you have the talking stick, Anurag. Go.
Thank you. So I'm basically going to talk about, building on what Pete talked last week on basic of smart grid and power system. And in terms of control, I'm going to talk about, decentralized or local control and also centralized control. So with that, next slide, please. I think I cannot change the slide, right?
Sorry, it's taking a second for it to register. I tested it before we got here.
Right arrow.
I'm using the right button.
All right. So before we control something, of course, we need to know that what we are doing to control and what's the goal. In the power grid, we are planning to basically have a reliable grid with economics, and resiliency is kind of new term, and sustainability, especially given the more and more renewable energy and demand response being integrated. So the way we do it is, we have all our physical assets in the field, and we sense a lot of measurements from there, and we get to the substation first, which will have some kind of control room, and all the measurements are get collected, and then we send it to a control center, like IT place, server room, and then from there we have several device, software tools like EMS and DMS, which help us in making a control decision. And sometimes there are local control, which is all embedded here, like a generator at old power control, which will take automatic control decision right here, or sometime in limited coordination way. So to operate our grid, we have to first sense, which are a bunch of sensors here, then communicate either locally to the controllers or to the control center server room. Then we need to do a lot of analysis and compute the status of the grid and any decision control variables. We also need to visualize those for the operator, and then send the control signal back, which is more optimal and control at centralized level, or which is more faster at local level. And when you say smart grid, I mean, of course, we have been doing this from more than 50 years. With advancement in sensing, like a PMU, a smart meter, and smart switches, all those different kind of sensing devices, with advancement in communication, which Carl will talk about soon, the ability to do more coordinated control and more optimal control has been, of course, increasing. And there has been a lot of research on human aspects too, that how an operator will make a decision or based on the data that we give to them. And with those advancements in a smart grid, there are more couple cyber physical kind of analysis need to be done before we take control decisions. All right, so I'll move on to next slide. So just like any other infrastructure, before we make control decision, we need to know that, okay, how much time we have to make a control, how much bandwidth we have in terms of communication, and all those different kind of things. And since we are trying to do the control for the power grid here, so we have to look at that what we can control and what we cannot do. So for example, wave effect, which is basically example is like lightning caused over voltage in the system. These kind of things we can only handle or manage locally, because there's no way that we can put the control which can respond in coordinated manner in milliseconds or microseconds. So lightning arrestor we put, which is not a kind of control, but minimize the impact of that. Switching over voltages, which is called in time frame of milliseconds, we can put some control devices for that, also locally. Fall protection, we know it's only local, and since it allows us to few cycles, so a couple of milliseconds, sometime, we can make it coordinated, which is still local, but kind of decentralized coordination in protection. Then there's electromagnetic effects in machine windings, which is also in order of milliseconds to seconds. Stability could be different kind, voltage or frequency or angle, and still we don't have any centralized control scheme for the stability. If it is not a voltage stability, for angle stability and for frequency stability, generally we have to put something local and coordinated. For voltage stability, we do have more time, and we can use a centralized approach to control that. Of course, it depends on some of the voltage stability happening because of a lot of component outages could be really fast, and should have a different kind of voltage stability schemes there, control schemes. Tie-line load frequency control is in seconds order. Economic load dispatch, that's where we do at centralized level, and that one is generally done in the control center. Then thermodynamic changes from boiler control, which is slow dynamics. It can happen seconds to hour, but still we do it in terms of local, because we don't need to do the centralized control for boiler control action dynamics. Load management, load forecasting, generation scheduling is done in several hours. And maintenance is months to year. Then expansion planning, which is done as a part of the planning. There's no control there, is in years. Now we can have for example, a resilient analysis. Resiliency can be embedded in transmission expansion planning, saying that we will accept those transmission line which will make the system more resilient to outage or blackout. So those concepts can be embedded here, but generally all of these are in planning stage. And here, once we get to this point, these are some centralized control, and then you get to the local control. Right, next slide, please. So if you look in the system level, in the control center, we have several visualization windows where you see the system and data, and operator consoles. That's where we make a centralized control decision. The data all come from the sensors, for example, like a PMUs with the communication link and remote terminal unit, or these days it's being replaced with some more like a digital devices, something like this. And then we collect this here, and then finally, we have a lot of data exchange from the neighboring control center or neighboring control areas using ICCC protocol. And we have also open access system information exchange with different participating entity. So that's where we put a local control, like for example, the data will be collected from here and decision will be made in other controllers here, and coordinated is also right here. On the next slide, please. So like any other infrastructure or field, the control basically depends on unobserved response and observed response. So we can take control action only based on observed response, or we can estimate some of the unobserved response. So for example, state estimation is the first thing which will estimate some of the parameters like angle, which is not there if you don't have a PMU. So using this observed response, we can make some automatic control, which is again local control. We make some system level operational control, which is at the control center. And also we do a lot of system planning using the same set of data, which is in long term. So different parameters that we are trying to observe and control is voltage, currents, power flows. We also get state of circuit breaker, and we try to control those as a control output. Then frequency, generator outputs, and also transformer type position for voltage control. So next slide. Most of these controls are, you can classify that as preventive or corrective actions. As it's evident from the name that generally you'll be doing preventive before things happen. For example, power system security analysis, the way we define in power grid is preventive action, because you kind of think ahead that if these contingency happen, what will be the impact on the power grid and what kind of control action we should be taking. So we do those as a kind of planning studies in advance to decide the control actions, and sometimes based on experience too, and then make a list of contingencies and decide the control action based on that. So security analysis against probable failure is a preventive mechanism. Sometimes human operator will do the same kind of control action. And then, of course, in long term, we do a lot of planning studies and forecasting to help us and make a proper decision as a preventive action. Corrective action, for example, protection is a corrective action because it happens after the fault happens, and we want to isolate the faulty part as soon as possible. Those are local action and could be decentralized coordinated. For frequency voltage stability control, we have local, we have some kind of decentralized, and also for voltage stability, centralized control action. Most of these things happen after the you see that voltage is not within the limit or it's drifting away. So remedial action scheme is an example of coordinated local control, where you get the data from several substations, and or maybe just one substation, but more than several measurements is used, and it does not have a system level information, but at least subsystem level information to take those control action, and generally you trigger those in worst scenario condition. Then an example of wide area control, which is kind of rare in actual system, but a lot of research has been done, is also coordinated control, but still faster. System restoration, of course, we do that after the system outage, and then human operator helps in taking corrective mechanism too. So we'll go to the next slide. So in a sense, based on what we just talked about, you can classify the existing control basically like a centralized or local. And in centralized control, which are basically, you can say that because you need a lot of data to communicate and send and process those, so it's slow and suitable for some of those control action like economic dispatch or the secondary voltage control, and those kind of things is okay. But we cannot use that for like a transient stability control, because we really need to take action really fast. It's generally not scalable because once we use mathematical approaches in a control center, we have to process a lot of variables, and if the system size increases or system data point increases, sometime we'll face the problem of not solving the optimization problem in time. Generally, it's optimal, and because we do have all the data to make a decision for optimal control, and that's why it's prone to failure if because it's single point of system analysis, and if the server is failed or data is not there, we cannot make a decision. So, for example, state estimation and security analysis may not work because the data is not there to make the state estimation to converge. And then we have a lot of local, like a protection, primary control, which is fast, but it's not optimal. It does not have a system level view. Generally, it's a hard-coded if you talk about remedial action schemes, predetermined settings for protection, and things are of course changing. I mean, adaptive protection is which is not hard-coded, but it still does not have a system level view. And for unexpected, because it's designed and predetermined for unexpected system scenario, it may not work. And in fact, we probably all know that protection system is one of the reason or #1 cause of blackout, because sometimes it will take action which it should not have taken. And then things are evolving. So like adaptive protection, PMU-based wide area control, which is a kind of distributed, coordinated, and hierarchical control, or evolving control, which is somewhere in between these two, which is fast, scalable, and suboptimal, but still have system level view, which could be fault tolerant, and of course uses a lot of data from system level and measurements, and it can support in line with Internet of Things if we think about a lot of data. All right, so we'll move on to next slide. So here's an example of local control. You can see that this one is generator level control. You have a generator, a turbine to run that, mechanical power coming from here, and the electrical power is being generated from here, going to transformer, and then finally to the grid. From here we get the measurement systems, so transformer like CT and PT. Then we can rectify or filter it as needed, and then we can use that for voltage control. So voltage is coming as where the setting is, or part we'll call automatic voltage regulator, and that generally is done through excitation field control. So that's where it goes in. And then we also look at turbine for the like a frequency control and ACE area control, which is area control error. And here also we'll have interconnection line power, which is looking at the frequency power exchange between the different control areas to make a decision on putting more power in. More mechanical power means frequency is increased, less mechanical power, frequency is decreased as needed. So the goal is to match the mechanical power and electrical power being produced so that frequency is good. So this is all like a frequency, and we can have a primary and secondary regulation. Primary should be very fast, and secondary is also in seconds. So here's an example of local control, and we'll move on to next slide. So other than protection, automatic voltage regulator, automatic generation control, remedial action scheme is also kind of local control, although it's a little bit coordinated. Under frequency load setting is another example of local control, and this is like a group control, which is also local control, because each which is good thing about frequency is that it's a kind of system level measurement, and each generator can respond to a frequency in a distributed manner but still having a system level view, because frequency is a system level measurement, while voltage is not. Different thing again we are trying to do here is the voltage, frequency, and power flow control. And we'll move on to next slide. So talking about centralized control, we used a control center picture from Pete's slide from last week. And that's a good example of centralized level control. You get all the information at control center and make a decision. Or sometimes you don't need to make a decision control because everything is good and system state is normal. So we'll talk about some example of centralized control in some of the next slides. So centralized control is based on two concepts. One is to know that in what state we are operating, that's situational awareness, and then making a control decision, which is a decision support. So all of this is generally done through operator, and we hardly have automatic control, but we might have in centralized level. And a lot of different things we need to think about when thinking about centralized control. For example, time frame, how fast we need to make decision. Is in seconds, minutes, hours, day, or months. When you think about ownership, that the control decisions that we're going to make is going to impact investor-owned assets, or public-owned, or independent power providers, or it's a co-op. And a lot of cases, like for example, ISO will not have control over generation assets. So they will send a signal, but they don't have ability to control it directly. They will send a signal, and then generally it might be set up for automatic control to do that. And sometimes we cannot do the control because you don't own the assets. Then we have to talk about think about geographical regions, that it is under the control area, or it is going all the way to reliability coordinator. It is interconnection level, which will make it more complex as you see it, the broader or wide area view. Different assets we are trying to control. Is it generation, is it transmission, or distribution assets, and what kind of transformer, who owns it? And of course, regulatory framework. Is it vertical, which is no market system, or it's a market system? So for example, the control in PJM will be different than control in Washington state. And then of course, what kind of parameter we are trying to control is voltage, frequency, and power flow. Power flow can be controlled in a slower manner. Voltage can be in a little bit slower. Frequency should be controlled faster. And we'll move on to next slide. So in the situational awareness, our goal is to look at all the data. So our goal for the tool to give the situational awareness is that we are processing a lot of data and operator cannot process it. So how to show it in best possible way, so it will help in making a human in the loop kind of control decision. And generally it's done using SCADA. So SCADA help us to get all the sensor data coming from CT, PT, current and voltages, PMUs to status, and then merging into RTU or PDC merging units. We talked about communication system, data archival historian. State estimation is generally the thing that you do if you're bigger than certain size utility, you have to do it. And then control center display organization is the way it's done is different for each system operator. And goal is to have the alarm and alerts, because one human mind cannot process all the information, but they can see alarm and alerts and decide that which one to act on. So next slide. And the second thing is decision support, which is decision support for real-time operation, short-term planning or long-term planning. And again, we have to look at seconds, minutes, hour, day, months. But generally, we do optimal power flow kind of analysis at the control center level. which will tell us the decision variable output for either dispatching the unit or committing the unit, or hydrothermal scheduling, security analysis, and it uses a lot of information from load and price forecasting, energy interchange, and market power analysis. Next slide. So in each control center, operator task generally varies, but typically there will be interchange operator, which will monitor all the power interchange between different balancing areas. There will be balancing operator, which will monitor generation with matching expected power demand. There is a transmission operator, which will monitor all this transmission switching, monitor system line loading and voltage conditions. There will be reliability coordinator, looking at stability and reliability of multiple areas. Also coordinating task between the multiple entities and of maintaining the reliability as required. And then we might have market operators, which is looking to purchase or sell current and future energy assets, so maximize the profit for that system. And also it should have understanding of NERC standards and constraints for renewable operating. All these operator tasks are really, really tough because they are trying to control something which is invisible, travels at speed of light, and which might be dangerous for the system if you don't control it properly. But the good thing is that we have enough local control which protects us. That's why we have protection. And a lot of these control under frequency control and remedial action schemes which will work if you don't take action on time. Okay, next slide. So operator will basically act on alarm to decide that what control action need to be taken, if any, and also send the control signal for all this substation and transmission system voltages to ensure voltage is within limit. Also scheduling of preventive maintenance, react to the non-forecasted event, which is more the challenging task. Coordinate with generator operator when the units are either coming online or offline. Also work with engineering to make sure that existing equipment or cable is approaching its limit. And then also prepare the contingency plan for scheduling outages, which generally comes from the planning division to them. And sometimes review the impact of proposed schedule outages. Next slide. So let's talk about evolving control. We talked about local, and then we talked about centralized. One example of evolving control is, a lot of concept out there. One which has been demonstrated in pilot phase is like a transactive control. And what it is basically is a means of using economic signal or other incentive to engage all the devices in the system, all the way from consumer to transmission system. And generally, consumer was less and less involved in the past. The concept was to follow the load, but now we can, do the demand response and other kind of local or behind the meter kind of solar control using this kind of transactive control. And it is possible to do that because we have more communication and more data points now, which was not possible earlier. Next slide. So in transactive control, the goal is to respond to system operation, and by engaging all the resources. And since you are going to operate at closer time frame, it's kind of you don't need to assume deterministic, and you can easily embed a stochastic model in that, and use local condition but with global information. Of course, forecast is very important, but short-term forecast is generally accurate. And goal is to coordinate operation of distributed assets to meet the objective of the overall grid, which is a generation, transmission, distribution, and manage all the controllable assets at the given time based on their availability and their bid. So we'll go to next slide. So as you can see here that you know, all the local assets, which is all the way till home and buildings, get involved in that, and the signal can flow based on status and opportunities from here to the, so it's an iterative process. So first this flows to the overall system level, and then need from the system will flow back asking that can you respond, and then they will respond back as we can respond in 1 hour, next 1 hour, or next 30 minutes, and then the control signal flows back to them to use those assets. So the time frame is shorter, accuracy is higher, and in few iterations we converge onto the goal in more reliable and sustainable way. Okay, next slide. So you can say that transit control is a distributed way to respond, but it has a system level view. Incentive signal can come from anywhere, even from big wind farm or transmission constraint. A big weather event is coming, you'll generate a signal and seek response from all these controllable assets. And like I said, it's a iterative process. So you start with opportunity, and then you do the incentive signal, and then modify incentive signal, and then get the feedback control signal back. Okay, next slide. Since CREDC is all about resiliency, so I thought we should talk about resilient control. First thing is that what's the difference between reliable and resiliency? So all the control that we just talked about, which exists now, centralized or local, all focus on reliability, which generally means a measure of operational consistency or performance in meeting connected customer load, which means that supply all the connected load. And we measure it in terms of several different factors, CREDC, CFE, MEFE, which tells us that, okay, how good we are meeting the load and how much power outage we generally have. Generally, we don't differentiate between the load. We give equal priority to all the connected load. While resiliency is more about reliability under extreme contingencies, which means that we are going beyond simple n-1 kind of things that exist in reliability and the way we do it right now. And we assume that when the extreme contingency happen, your system cannot be reliable, which means we cannot provide, like under cybersecurity attack or under the hurricane or extreme event scenarios, we cannot provide all the connected load. So that's why we need to define the resiliency concept, where we think about priority of critical load and we only talk about critical loads to supply the power to them, not the non-critical load. And it tells the kind of indication of preparedness for a network to withstand extreme contingency or extreme scenarios that can happen in the system. Generally, there is no formal metric so far, but we need to have so that we can know that how resilient our system is. And next slide. Designing resilient control is a very difficult task because we need to model all the different things that can happen, because you're talking about extreme things that can go wrong and in shorter time frame. So you do need to model like a weather impact, which can be seen in something like a power world visualization, but weather impact need to be modeled in several software. We need to do power system analysis, of course. We need to do dynamic analysis. We need to model control, all working together in a single simulation. We need to model protection in that. Cyber modeling tool, we need to do that, which is cybersecurity model, communication model, all the protocol, and then contingency modeling tool, and then interfacing in all of these. And then only we can design a good resilient control to handle, let's talk about like transmission cascading outages. To do that, it can be triggered by any of these, like system transient stability, voltage stability, It could be because of cyber, it could be because of protection. That's why we need to model all of these so that we are resilient to cascading outages. All right, next slide. So in the future grid, things will be different. We'll have more integration of renewables and a lot of active endpoint data point to control and not to be controlled. And to do the control, the scalability that we need in this existing control is a lot. Our optimal power flow cannot take a single optimization problem cannot take all of these new data points. We'll have a new economic mechanism because of demand response, because of renewables, because of the way building can respond, and that's why the business model and economic mechanism will be different. So what we need is basically on the next slide. We will, of course, need more variability management and forecasting tools to handle or manage stochastic control or probabilistic kind of control more embedded in the system. We need to integrate demand response management with EMS integration. We need to integrate EMS and DMS because the time frame is getting shorter and shorter, and that's why we need to integrate all these things and not have a single tool, but exchange the data to impact that. We need to integrate all this PMU level analysis. ID data need to be managed and handled more intelligently. We have to utilize this faster communication because it exists. All this new sensors are not being used in optimal way as possible. We need to look at not only synchronous time measurement from PMU, but use a GPS signal to additional sensors, additional substation, and additional time based measurement. Resiliency metric need to be used if we want to go towards the resilient control, and value need to be also assessed. That how do we give value to that? How much we are getting out of by integrating this resilient control. Then decentralized and coordinated control, and of course fault tolerant and cyber resilient delay aware kind of control is needed. That was my last slide, and the next slide is just an acknowledgement slide. I'll be ready for any questions.
This is Stuart Madnick at MIT.
Sure.
Can you hear me? So you mentioned in one of the last slides here, you talk about the issue of possible cyber attacks, which obviously is one of the areas that many of us are interested in. I have two questions. As you go to more and more rapid response and more automated systems in order to handle or in order to be in smart grid, have you thought much about what additional risk factors occur either in the possibility of controls being taken over or sensors being deceived, leading the system to behave in ways that in retrospect don't work well, but based upon disguised sensor readings make sense? Are those things you've looked at much?
Yeah, I mean, in terms of research, yes, we looked at WSU and a lot of our researchers in CREDC are doing that. And that's a very critical point, and that's one of the kind of limitation that utility right now have to go for automatic control. And if you look at, like, let's say PMU based automatic control, it's hardly happening in the utility because they are afraid of that. So in terms of analysis, and that's why I put the cyber resilient or cyber attack resilient control, which is still open problem. And we have to we are designing, and we have to keep designing those and come up with the schemes which really works.